Comparison between linear motion and rotational motion considering dimensional analysis. Left hand side linear motion, right hand side rotational motion. Number one, we should know what is linear displacement. Linear displacement. Linear displacement is denoted by S. S is the linear displacement or distance traveled by the body linearly. S is equal to L, which is the linear displacement or linear distance traveled by the body in linear motion. So that's why we can write S is equal to L, which is the linear displacement, which is the linear displacement or linear distance traveled by the body in linear motion. S is equal to L, which is the linear distance, that is length of an arc when a body is revolving in a circular orbit. Right hand side we can write angular displacement. AB is an arc. AB is an arc. So here AB is the arc and O is the center of the arc. The arc AB makes an angle theta. Arc AB makes an angle theta with the center O, and L is equal to S, which is the length of the arc or linear distance traveled by the body. R is the radius. Theta is equal to L by R. That is angular displacement theta is equal to length of arc L divided by radius R. Theta is equal to L by R. Theta is equal to L by R, which is the angular displacement, which is the angular displacement of the body, that is angle. Theta is equal to L by R, which is the angle or angular displacement of a body moving in a circular orbit. Here, that's why we can write theta as equal L into R. Theta as equal L into R, and here dimension of S will be what? Dimension of linear displacement will be equal to L, capital L on the right hand side, and here dimension of S or dimension of linear distance or displacement will be L. Dimension S is equal to dimension L, that is the dimensional formula of linear distance traveled by a body in linear motion. On the right hand side we can find the dimension of angular displacement, that is dimension of theta is equal to dimension of L by dimension of R, equal dimension of capital L divided by dimension of capital L, which will be equal to 1. Therefore dimension of theta is equal to 1 means angular displacement is dimensionless quantity. Dimension of theta is equal to 1. That's why what we can say, the angular displacement theta is dimensionless quantity. Dimensionless quantity. And unit of theta, unit of angular displacement theta is radian. Now we can compare linear velocity and angular velocity in terms of dimensional analysis. R is the radius of circular orbit. We have a body at the point A at instant t equals 0. The body revolving anti-clockwise in horizontal circular orbit at the point B, that is at instant t equal t second. The body will be at the point B, and at the point B, the body will have tangential final velocity v. V is the tangential final velocity at the point B at instant t equal t second. Left hand side we can write linear velocity or tangential velocity as equal s by t. S is the linear distance or length of arc of the body revolving in circular orbit. And v is equal to s by t means linear distance by time or linear displacement by time, which is the tangential velocity or linear velocity of the body. Tangential velocity or linear velocity of the body. On the right hand side, angular velocity is omega, which is theta by t, where omega is angular displacement theta divided by time t. Now in the diagram, the body is revolving in horizontal circular orbit anti-clockwise at the point B. The body has the tangential velocity v along this direction and angular velocity will be omega. Angular velocity of the body at the point B, omega, will be acting vertically upwards. That's why the relation between linear velocity and angular velocity is what? V equal to omega r. That means V is equal to omega into r. That is tangential velocity V is numerically equal to the product of angular velocity and radius of the circular orbit. That means vector V is equal to vector omega cross vector r. Vector V is equal to vector omega cross vector r. Now we can write down the dimension of tangential velocity. Dimension of tangential velocity V is equal to L t to the power minus 1. Dimension of tangential velocity is V equal to L t to the power minus 1. On the right hand side, dimension of omega is equal to dimension of theta by dimension of t, which is equal to 1 by dimension of t. That's why what we can write, dimension of omega is equal to t to the power minus 1. Dimension of omega is equal to t to the power minus 1, which is the dimensional formula of angular velocity of a body revolving in a circular orbit. Dimension of omega is equal to t to the power minus 1, which is the dimension of angular velocity. Now we can compare tangential acceleration and angular acceleration. Left hand side we can write tangential acceleration. On the right hand side we can write angular acceleration. On the right hand side we can write angular acceleration. In the diagram, this is a horizontal circular orbit. O is the center, R is the radius, and the body was at the point A. The body of mass M was at the point A at instant t equals 0 second. At the initial point A, the body has initial tangential velocity u. U is the initial tangential velocity, A is the tangential acceleration, and omega 1 is the initial angular velocity which is acting vertically downwards. The body is revolving anti-clockwise, and again the body will move to the point B at instant t equal t second. The body will move to the point B at t equal t second. We can denote the angular displacement theta. Theta is the angular displacement at the point B. The body has final tangential velocity v, and acceleration, tangential acceleration will be a. V is the final tangential velocity. At the point B, final angular velocity is omega 2. Omega 2 is the final angular velocity of the body at the point B. Alpha is the angular acceleration. Alpha is the angular acceleration. And here omega 1 is the initial angular velocity. Initial angular velocity of the body at the point A at instant t equals 0 second. And here omega 1 is the initial angular velocity, and omega 2 is the final angular velocity of the body at the point B at instant t equal t second. Omega 2 is the final angular velocity of the body at instant t equal t second. Left hand side we can write tangential acceleration A is equal v minus u divided by t. A is equal to v minus u divided by t, which is the tangential acceleration, which is the rate of change in linear velocity with respect to time. That means v minus u is the change in velocity divided by time, which is the tangential acceleration of the body revolving in a circular orbit anti-clockwise direction. On the right hand side we can write down the expression of angular acceleration. Alpha is the angular acceleration, which is omega 2 minus omega 1 divided by t. Alpha is equal to omega 2 minus omega 1 divided by t, which is the expression of angular acceleration. Now what will be the mathematical relation between tangential acceleration and angular acceleration, which is A equal alpha into r. That means tangential acceleration vector A is equal angular acceleration vector alpha cross vector r. vector A is equal to vector alpha cross vector r. That means tangential acceleration is equal to the cross product of angular acceleration vector and radius vector. Dimension of tangential acceleration A is equal to L t to the power minus 2. Dimension of tangential acceleration is L t to the power minus 2, and then dimension of angular acceleration alpha is equal to dimension of omega 2 minus omega 1 divided by dimension of time t, which is equal to dimension of omega 2 divided by dimension of time. As dimension of omega 2 minus omega 1 is equal to dimension of omega 2 is equal to dimension of omega 1. Since omega 2, dimension of omega 2 is equal to dimension of omega 1, that's why we have written omega 2, dimension of omega 2 in place of dimension of omega 2 minus omega 1. In place of dimension of omega 2, we can write t inverse divided by dimension of t. Therefore, dimension of alpha is equal to t to the power minus 2. Dimension of alpha is equal to t to the power minus 2. So, this is the dimensional formula of angular acceleration. Dimension of alpha is equal to dimension of t to the power minus 2, which is the dimension of angular acceleration. Dimension of angular acceleration. To find the dimension of moment of inertia, we have to compare mass and moment of inertia. On the left hand side, we can write mass. On the right hand side, we have to write moment of inertia, mass and moment of inertia. In the diagram, AB is the axis of rotation about which a body will rotate. This is the circular orbit. O is the center of this circular orbit. We can denote the perpendicular distance or radius of the circular orbit. Here r is the perpendicular distance of a body which will be revolving around the axis from the axis of rotation. So this is the body of mass m, and r is the perpendicular distance. The body is revolving around the axis AB with tangential velocity v and angular velocity omega. Omega is the angular velocity, and the body revolves anti-clockwise with the angular velocity omega. And in this case, moment of inertia I is equal to mr square. Moment of inertia is I, which is numerically equal to the product of mass and square of perpendicular distance. I is equal to mr square. I is equal to mr square, which is known as moment of inertia of the body about the axis of rotation AB. Moment of inertia of a body of mass m which revolves with the angular velocity omega about the axis of rotation AB, about an axis of rotation AB. On the left hand side, mass is m is the mass of the body, and common relation between them is I equal to mr square. I is the moment of inertia, and which is equal to the product of mass and square of perpendicular distance of the body from axis of rotation. That's why moment of inertia can be written as mass into under bracket perpendicular distance of the body from the axis of rotation, bracket close, square. In this case, mass is comparable to moment of inertia. Mass in linear motion is comparable to moment of inertia in rotational motion. So that's why what we can write, that is moment of inertia plays the same role. Moment of inertia of a body about an axis plays the same role in rotational motion plays the same role in rotational motion as played by the mass in linear motion. Played by the mass in linear motion. Moment of inertia under bracket I plays the same role in rotational motion. As played by the mass in linear motion. Now the dimension of mass m is equal to only capital M. Dimension of mass m is only capital M. Whereas on the right hand side we can find the dimension of moment of inertia. Left hand side, dimension of mass small m is equal to dimension of capital M. So that is the dimensional formula of mass. On the right hand side we can find the dimension of moment of inertia, that is dimension of I is equal to dimension of m into dimension of r square, which is equal to dimension of m into dimension of l square, is equal to dimension of I is equal to ml square, m into l to the power 2. Dimension of I is equal to ml to the power l square or l to the power 2. I is equal to ml square under bracket I is equal to under bracket ml square. That is the dimensional formula of moment of inertia. That is the dimensional formula of I is equal to ml square. Dimension of I is equal to ml square, which is the dimensional formula of moment of inertia. Mass is a scalar quantity, whereas moment of inertia under bracket I is neither a scalar nor a vector. Mass is a moment of inertia is a tensor. To find the dimension of angular momentum, we have to compare linear momentum and angular momentum. On the left hand side we can write linear momentum. On the right hand side we have to write number 5, that is angular momentum. Right hand side we can write angular momentum. So to find the dimension of angular momentum, we have to compare between the linear momentum and angular momentum. This is a circular orbit, horizontal circular orbit. O is the center and we can denote the radius. R is the radius of the horizontal circular orbit about which a body will be revolving anti-clockwise direction. R is the radius, and this is a body of mass m at the point A. This is a body at the point A at instant t is equal to 0 second. At instant t is equal to 0 second, the body was at the point A. Body revolves anti-clockwise. And the body has initial velocity as u. And that is 0. Here we can assume u as 0, and the body will be at the point B at instant t equal t second after traversing an angular displacement theta. At t equal t second, the body will be at the point B on the circular orbit, and at the point B, tangential velocity or final linear velocity will be v. Along this direction, along this tangential acceleration, velocity will be acting, and now we can denote angular velocity, that is omega, as the angular velocity of the body at the point B. Angular velocity omega acts vertically upwards, and we can denote the angular displacement. Theta is the angular displacement of the body if it revolves around the circular orbit. P is the tangential linear momentum at the point B, and also we can denote angular momentum L. Which is acting vertically upwards provided the body is revolving anti-clockwise. P is equal to mv, which is linear momentum, and this linear momentum acts tangentially with respect to the horizontal circular orbit. P is equal to mv, which is the linear momentum. That means linear momentum P is numerically equal to the product between the mass and linear velocity. P is equal to mv, which is the linear momentum or tangential momentum. On the right hand side, we can write L equal to I omega. L is the angular momentum, which is equal to the product of moment of inertia I and angular velocity omega. I omega is equal to the angular momentum L. L is equal to I omega. L is equal to I omega, which is the angular momentum of the body revolving around the axis AB. Linear momentum P is equal to mass into velocity. Now mass m is comparable to moment of inertia I, and tangential velocity V is comparable to angular velocity omega. Angular velocity omega. Now angular momentum L is equal to R into P. That means vector L is the cross product of vector R and vector P. Angular momentum vector is equal to the cross product of R and P. Dimension of linear momentum P is equal to dimension of linear momentum P is equal to ml t to the power minus 1. Whereas on the right hand side, here dimension of P is equal to ml t to the power minus 1. Now on the right hand side, what we can write, and here dimension of P is equal to ml t to the power minus 1, which is the dimensional formula of linear momentum. This is the dimensional formula of linear momentum, or dimension of linear momentum. Whereas dimension of angular momentum L is equal to dimension of I into dimension of omega is equal to dimension of m L square into t to the power minus 1. That's why we get dimension of L as equal dimension of angular momentum L will be ml square t to the power minus 1. Dimension of angular momentum is ml square t to the power minus 1. Dimension of L is equal to dimension ml square t to the power minus 1, which is the dimensional formula of angular momentum. Hence dimensional formula of angular momentum is ml square t to the power minus 1. To find the dimension of torque, we have to compare force and torque. Torque is comparable to force. Torque plays the same role in rotational motion as played by the force. Force F is equal to ma, and this is a body of mass m. If a force is applied on the body will be moving with the acceleration a. That means due to application of force, the body will have linear motion. Due to application of force, the body will have linear motion. That means the body gets linearly displaced due to application of force. Due to application of force, the body will have linear motion and gets tangential acceleration or gets linearly displaced. On the right hand side, we can draw a body. This is a rigid body which has fixed point O. O is the fixed point of the body about which the body can rotate. Here O is the fixed point about which the body can rotate. Now we can draw an imaginary line. This is the line along which a force is applied such that the body will rotate about the fixed point. AB is the line of action of force along which a force F is applied along this direction. Now we can denote the perpendicular distance. This is the perpendicular distance. That means ON is the perpendicular distance of the fixed point from the line of action of force. Now we can denote the oblique distance. This is R is the oblique distance. That means OP is the oblique distance of line of action of force from the axis of rotation. Theta is the angle between the oblique distance r. Theta is the angle between the oblique distance r and the extended line of action of force in backward direction. The body will rotate anti-clockwise about the fixed point O under the action of force along the line AB. The body will rotate anti-clockwise about the fixed point O, provided the force is applied along the line of action of force, that is along AB, and there is fixed point. Now torque is equal to the perpendicular distance of line of action of force from the axis of rotation into the magnitude of force. Torque is the perpendicular distance into force, and here perpendicular distance of the perpendicular distance is the perpendicular distance of fixed point O from the line of action of force, that is from the line AB. Torque is the product of perpendicular distance of fixed point O from the line AB of action of force into the magnitude of force. Therefore, tau is equal to On into F. Therefore, tau is equal to R sin theta into F. Since sin theta from the right angle triangle ONP, sin theta is perpendicular ON divided by hypotenuse OP. Therefore, tau is equal to RF sin theta. That is the expression of torque. Therefore, torque tau is equal to R sin theta into F. Torque tau is equal to R sin theta into F. Here R sin theta is equal to the perpendicular distance ON. R sin theta is equal to ON. R sin theta is equal to ON, which is the perpendicular distance of the fixed point O of the body, from the line AB of action of force, from the line under bracket AB of action of force under bracket F. Dimension of force F is equal to ml t to the power minus 2. Which is the dimension of force, and on the right hand side we can find the dimension of torque tau. Dimension of tau is equal to dimension of R into dimension of sin theta into dimension of force F is equal to dimension of L into 1 because dimension of sin theta is 1 into dimension of force. So here dimension of sin theta is 1 because sin theta is dimensionless, and in place of dimension of force what we can write ml t to the power minus 2. So finally we get the dimension of torque tau as equal ml square t to the power minus 2. Dimension of torque tau is equal to ml square t to the power minus 2. That is the dimension of torque. Dimension of torque or dimensional formula of torque is ml square t to the power minus 2. And on the left hand side, dimension of force is ml t to the power minus 2. Dimension of force or dimensional formula of force is ml t to the power minus 2. That is, this is the dimension of force. We can describe alternative process to find the dimension of torque. Now force is equal to mass into acceleration. Force is equal to the product of mass and acceleration F is equal to ma, which is the force acting on a body, of mass m moving with the tangential or linear acceleration a. F is equal to ma, which is the force acting on a body of mass m moving with linear acceleration a. Whereas on the right hand side we can write torque. Torque tau is the product of moment of inertia I and angular acceleration alpha. Tau is equal to I alpha, which is the torque. Due to application of torque, a body revolves or rotates, and the body will have rotational motion due to application of torque. Tau is equal to I alpha, which is the torque acting on the body of moment of inertia I. So now we can find the dimension here. Alpha is the angular acceleration of the body revolving in anticlockwise direction in a circular orbit. Alpha is the angular acceleration. Now force is comparable to torque. Mass in linear motion is comparable to moment of inertia I in rotational motion. Tangential acceleration A is comparable to angular acceleration alpha in rotational motion. Dimension of force is equal to ml t to the power minus 2. And we can find the dimension of torque. So dimension of torque, that is dimension of tau. Dimension of torque tau is equal to dimension of I into dimension of alpha is equal to dimension of ml square into dimension of t to the power minus 2. Therefore, dimension of torque tau is equal to ml square t to the power minus 2. Dimension of torque tau is equal to ml square t to the power minus 2, which is the dimensional formula of torque.